This meeting is being recorded.
So, welcome everyone to this week's talk in the virtual geometry and geometry with symmetries. So it's a pleasure to welcome my colleague Katie Gittins from Durham University, and she will talk about nodal counts for the roving problem on Lipschitz domain. So it's a pleasure to have you, Katie.
Thank you very much, Fernando, and thank you everybody for coming as well. So hopefully you can hear me okay and see my slides. Good. If you have any questions throughout the talk, please don't hesitate to interrupt me. I don't seem to be able to see the chat, so please feel free just to unmute yourself. So yeah, it's great to be here on this seminar. I'm going to tell you eventually about nodal counts for the Robin problem on domains in Euclidean space with Lipschitz boundary, but what I was hoping to do first was to tell you probably things you've already seen before about the Dirichlet problem, and then I'll move to the Neumann problem so we can see some of the obstacles that we face moving from Dirichlet to Neumann, and then eventually I'll come to Robin. So with that in mind, let me first fix my notation. So throughout the talk, omega for me will be a Euclidean domain in n-dimensional space, and it will be non-empty and open with finite measure. As I change the boundary condition later, I will add more constraints. And then we know, of course, the Dirichlet eigenvalue problem for our Laplacian. So I have Laplacian u is lambda u is 0 on the boundary in the weak sense. And we know that under these geometric conditions, that when the measure is finite, the Dirichlet spectrum is discrete, and we have the sequence of eigenvalues where we repeat them according to multiplicity. They're all positive. The only accumulation point is infinity. And the main thing I should tell you now is about the eigenfunctions, because I'll be interested especially in the eigenfunctions in this talk. So we, of course, remember that the Dirichlet eigenfunctions form an orthonormal basis for L2 of omega. And here the audience knows very well the famous question, can we hear the shape of the drum? And even contributed to the answer that there are domains that make the same sound but are not the same shape. We could, of course, ask ourselves, what can we hear, even though we can't determine the entire shape? And two of the results in that direction will be very helpful to us for this talk. So I'll just remind you of the Pleijel law for the Dirichlet eigenvalues. That tells us the asymptotic behavior of the eigenvalues as k tends to infinity. And we see how it depends on the volume of the domain omega, and the power there is k to the 2 over the dimension. And another result that will be useful for us that I can interpret as hearing some information is the Faber-Cran inequality. So that's in the spirit of shape optimization, where I wish to minimize the first Dirichlet eigenvalue among all open sets in Rn of fixed volume. And by Faber and Cran, we know that the minimizer is the ball of the same volume with equality if and only if the domain really is a ball up to sets of capacity 0. So we could interpret that in some sense as we can hear if the drum is a ball or not. So both of these results I will be using today, but what I promised to tell you about was nodal counts. So I should now remind you some definitions about nodal geometry. So here I have the definitions for a given eigenfunction u of the Dirichlet Laplacian on omega. The nodal set is the set of points inside omega where the eigenfunction vanishes. And then the nodal domains are the complement of that set where the eigenfunction has vanished. So if we picture your favorite set maybe in R2, then take your favorite eigenfunction, and wherever it vanishes, you use that to chop up the set into subsets. And I'll be interested in counting nodal domains for a given eigenfunction. So we remember that in the case of one dimension, when I have just the Dirichlet eigenvalue problem on an interval, we can, of course, compute explicitly the eigenfunctions. They would be sine functions. And there we know, of course, that then the kth Dirichlet eigenvalue always has exactly k nodal domains. So if I take an eigenfunction for the kth eigenvalue, It's something like sine 2 pi kx over L, where L is the length of the interval, and it has exactly k nodal domains. There's k minus 1 zeros inside. So in one dimension, we have this property that for the kth eigenvalue, there is an eigenfunction with k nodal domains. What happens in higher dimensions? So the example I will always come back to in this talk is the square, and I apologize that that's pretty much the only place where I could claim to have some symmetry for my geometry with symmetries talk. But here is the square, and in blue, you can see some nodal sets, so where the eigenfunction vanishes for certain eigenvalues. And now the eigenvalues, so the top left here is lambda is 5, corresponding to the third eigenvalue. Then I've got lambda is 50, for lambda is 100, an eigenfunction corresponding to that one, and then lambda is 1025. So these were just to show you some examples of how the nodal set can look as we change the lambda. Now, my choices might lull you into a false sense of security in some sense that it looks like as I increase lambda, the picture gets more and more complicated. So there are cases for the square where there are infinite sequences of eigenfunctions that have exactly 2 nodal domains. So it's not necessarily that each time I increase lambda, I make the picture worse. I don't necessarily increase the number of nodal domains. But the main reason why I'm showing you these examples is actually because of this very simple one here on the top left. So this one is lambda is 5. If you still remember your formula for the eigenvalues, the Dirichlet eigenvalues of the square, you'll notice that's the same eigenvalue as the second one. So lambda is 5 is actually the third eigenvalue for the square. And you see there that there are only 2 nodal domains. So it's different to our interval case. We can only have 2 nodal domains for the third eigenvalue. We don't have 3. And so you'll remember that this is a celebrated theorem of Courant, that for any function in the eigenspace corresponding to the kth eigenvalue, it has at most k nodal domains. So when we go to higher dimensions, higher than 1, we can only say there's at most k nodal domains. And the special case where we achieve k, so for the kth eigenvalue, there is an eigenfunction which has k nodal domains, we'll give that the special name Courant-sharp. So that means the eigenvalue or eigenfunction are Courant-sharp if there are exactly k nodal domains. So now would be a good time for me to convince you that this object, there are some eigenvalues which are Courant-sharp. So if we think first for k is 1, then by Courant's theorem, we know any eigenfunction corresponding to the first eigenvalue has at most 1 nodal domain. And of course, we know that the eigenfunction is not trivial. And so it has to have exactly 1 nodal domain. It's the one that doesn't change sign. And then if I go to k is 2, then Courant tells me there's at most 2 nodal domains for any eigenfunction. But we also have to have that the eigenfunctions are orthogonal. And if our eigenfunction has to be orthogonal to constant, of course, it has to change sign. And so that gives us 2 nodal domains. So both the first and the second Dirichlet eigenvalue, they're always Courant-sharp. But we already saw in the example of the square that the third one need not be Courant-sharp, because for the third one for the square, for example, any eigenfunction only has 2 nodal domains. So this Courant-sharp property is satisfied by some eigenvalues, but not necessarily all of them. So then that could beg the question, compared to the one-dimensional case, where we had infinitely many of these Courant-sharp eigenvalues, do we have infinitely many in higher dimensions, or do we only have finitely many? And this question was resolved by Pleijel, that if I would have a set in Rn, the finite measure, it only has finitely many of these Courant-sharp eigenvalues. So there's only finitely many lambdas for which the eigenfunction in the eigenspace has the maximum splitting, has the maximum number of nodal domains. And I'm going to state this theorem of Pleijel slightly more precisely now so that I can introduce nodal counts. So here my curly n omega d, that will denote the number of nodal domains of the eigenfunction that corresponds to lambda k. And then I can state Pleijel's strong form of the Pleijel theorem as follows. So for my given omega, the lim sup of this nodal count, the number of nodal domains for the kth eigenfunction, divided by k, is bounded above by a dimensional constant. And what's important about the dimensional constant is it's strictly smaller than 1. So we do have finitely many Courant-sharp eigenvalues. And I've pointed out here what the constant gamma n is when n is 2. It's 0.69, and because I'd like you to remember that one in the next few slides. So this constant in 2 dimensions is 0.69. But what I'd like to do next is to remind you of the proof of this theorem so that we can see what the hurdles and obstacles might be when later I change the boundary condition from Dirichlet to Neumann and to Robin. So just for dimension 2, let me remind you of the proof. So we'd like to show that the lim sup of the nodal count divided by k is less than gamma 2. In other words, that there are finitely many Courant-sharp eigenvalues. So let's suppose that we have lambda k and uk a Courant-sharp eigenpair, and I'll call the nodal domains omega 1 up to omega k. And then we notice, of course, that on each nodal domain, we still satisfy the eigenvalue equation, Laplacian u is lambda u. But also because these are nodal domains, the eigenfunction must vanish on the boundary of each one of them. And so that tells us that on each nodal domain, the function doesn't change sign. And we know that the only eigenfunction for which we don't change sign is the first one by the orthogonality. So that tells us that lambda k must be equal to lambda 1 of each nodal domain. So each of the omega i's. Okay, now the only information in this talk that I told you about lambda 1 was sneakily that there is the Faber-Crown inequality that we can always get a lower bound for the eigenvalue by replacing our domain with a ball. So let's apply the Faber-Crown inequality in practice with swapping each nodal domain omega I with a ball of the same volume. So we do Faber-Crown inequality here. And then I've just rescaled the eigenvalues so that they all have lambda 1 of the ball of radius 1. So just some rescaling at this step. So now that if we rearrange the inequality, it tells us something about the volume of omega I on this constant greater than or equal to 1 over lambda k omega. And if we add up over all the nodal domains, it gives us an upper bound for k over lambda k. But if I would now assume that there were infinitely many Courant-sharp eigenvalues, then I could send k to infinity in the right-hand side. And we know how lambda k behaves as k goes to infinity by the Weyl law. So if we do that, if we send k to infinity, the right-hand side tends to volume of omega over 4 pi. But we see that we need the opposite inequality to be true because of the magic value 0.6916. So if we would have had infinitely many Courant-sharp eigenvalues, we would have had a contradiction. Okay, so in the case of Euclidean domain, this is our strategy that we use the good properties of the eigenvalue problem, the fact that the first eigenfunction doesn't change sign, then we swap all of the nodal domains, omega 1 up to omega k, by disks of the same area, and then we arrive at a contradiction once we've applied Weyl's law. So we must have had finitely many Courant-sharp eigenvalues. I should mention here that the Pleijel theorem does also hold in the case of manifolds or domains in manifolds. This was proved by Berard and Meyer. And the argument there is different. There is this notion of a sort of almost Faber-Crown inequality, but I will say more about that when we get to the Robin case, because it turns out a similar idea is very useful there. But sticking with the domains for a little while longer, so you see that we in taking this inequality here, in applying Faber-Cran, we've effectively lost quite a lot of information because we started from some planar domain that need not have looked anything like a union of disks, and then we've replaced all the nodal domains as disks, and that looks like we would have lost quite a lot of information. So you could ask, how much better should this constant be? This constant can't be the best one because we lost lots of information, but what would the best constant be? So just for general interest, there were some improved versions of Pleijel's theorem, namely with improved constant due to Bogan, Donnelly, and Steinerberger, effectively using improved versions of Faber-Cran inequality in the same argument as Pleijel. But it does beg the question, what is the best Pleijel constant? So if I would define for my omega, p omega to be the lim sup of this nodal count over k, then we could ask what's the best constant. And there is a very interesting conjecture due to Polterovich that among bounded planar domains with regular boundary, the optimal constant should be 2 over pi. So you can see it's 0.637. It's quite a lot lower than our 0.69 that Pleijel's theorem gave us. So we have quite a way to go to get to this conjecture. A step forward in that direction would be if we could prove the hexagonal conjecture, namely that in our procedure of Pleijel that we just did, rather than swapping by disks, we could swap by hexagons. That would improve the situation to 0.67 rather than 0.69. Actually, this second conjecture is linked to another field of spectral geometry called optimal partitions, where there is a hexagonal conjecture over there. So if that conjecture could be proved, then we would get, unfortunately, my light's gone off. Sorry. If that conjecture could be proved for optimal spectral partitions, that the hexagon is optimal, then we would get an improvement in our Pleijel constant, but only as far as 0.67. That's as far as our Pleijel method could go, and then we would need some other method to try and get as far as the Polterovich conjecture. And I should mention the conjecture of Polterovich, the 2 over pi is attained through rectangles where the sides are related irrationally. Okay, so this was more an interlude because when I showed you the proof, I'm sure you wondered what's the best constant here. Unfortunately, I'm not now able to tell you that one of these conjectures is resolved because I don't know how to do that. So I'm going to go for a more modest question instead and ask, since I know that there are finitely many Courant-sharp eigenvalues, how many is finitely many? So how many Courant-sharp eigenvalues are there for a domain omega, and how big can they be? And so I'll start my story in this direction now, that we can get upper bounds for these Courant-sharp eigenvalues. And so there's quite a lot of information on this slide. So I'll try to skim over it to point out the main parts. So I'm still, for the Dirichlet problem, have a domain with finite Lebesgue measure. Then I define this quantity mu of omega. It's just the volume of an interior tubular neighborhood of the boundary of width epsilon. And then for our given omega, we define epsilon omega to be the infimum epsilon, such that this volume is bigger than some quantity that's related to our Pleijel constant gamma n. So you see there's some geometric constraint here. And then using in this framework, just for sets with finite measure, you can show that the largest Courant-sharp Dirichlet eigenvalue is bounded in terms of some dimensional constant times 1 over epsilon omega squared. And also that the number of Courant-sharp Dirichlet eigenvalues is bounded by some dimensional constant volume of omega on this geometric quantity epsilon omega to the n. So we can get bounds for these eigenvalues in terms of the geometry. But to give you a bit more information about this result, let me go to an example. And I'll go to the example of the square, because of course there we can compute things more, well, we know how to compute the eigenvalues and things. So for the square, if I would apply my theorem that we just saw, then I would have that the number of Courant-sharp eigenvalues is less than or equal to this rather big number, 710,000 and so. And when I gave this talk in person recently, this was the place where the audience started laughing. So if you're laughing now, please don't worry. Of course, we know for the square that we can compute the eigenvalues and eigenfunctions, and with some work and using symmetries as well, using reflections and properties of the nodal domains, we can show that there are just three Courant-sharp eigenvalues. So, okay, the bound isn't so good for the square because it has this horrible big dimensional constant out the front. But remember, the theorem was for any set with finite measure. So it could also compute an upper bound for less nice sets than the square, say for a von Koch snowflake. In that case, there's at most 15 times 10 to the 7 Courant-sharp eigenvalues. I have no idea what the eigenfunctions or eigenvalues look like for that one. So, but I would suspect that the constant is still playing a big role here. But we could ask ourselves in terms of the geometry, what does this bound tell me in terms of the geometry of the domain? So let me be a bit more precise. If I would add a hypothesis, or two hypotheses, so I would take an open, bounded, and convex set, rather than finite measure, if I take bounded and convex, then we can bound our number of Courant-sharp eigenvalues, again in terms of some big dimensional constant, but in terms of the geometry, there is the Hausdorff measure of the boundary appearing, and the volume of the domain. So we've effectively got some isoperimetric ratio on the right-hand side. So in terms of what the Courant-sharp eigenvalues could tell us about the geometry, if we already knew that our domain omega was bounded and convex with lots of Courant-sharp eigenvalues, so our C omega would be big, then that would tell us the isoperimetric ratio also has to be big, so the shape of omega should be long and thin, which feels like it's going back towards the interval in some sense, just that I'm in higher dimension. So in terms of the geometry, this result can tell us something. Okay, so now that we have some feeling for Pleijel's theorem and how big and how many Courant-sharp eigenvalues we have, I'll pass to the Neumann boundary condition, but maybe before I do that, I should just ask if you would like to ask any questions. Okay, very good. So let's then change the boundary condition. So just to set my notation again, this time omega has Lipschitz boundary. I've swapped the boundary condition for the normal derivative on the boundary is 0. We of course have our discrete spectrum, and mu1 is 0 because omega is connected. And again, we have Courant's theorem. So we can still introduce this notion of Courant-sharp. And again, the first eigenvalue is Courant-sharp, and so is the second one. But when we get to the third and higher, things can go wrong, and we don't always have Courant-sharp eigenvalues. But we could ask ourselves whether we do still have a Pleijel theorem. So in the case of the Neumann eigenvalue problem, are there infinitely many Courant-sharp eigenvalues or finitely many? So again, my curly n will denote the nodal count, namely the number of nodal domains for an eigenfunction corresponding to the Neumann eigenvalue mu k. And then I'll now try to tell you some of the background for the results in the spirit of Pleijel's theorem. So the first one was Pleijel in 56, that the square has finitely many Courant-sharp eigenvalues. And as you could imagine, the proof was using the explicit formulae for the eigenfunctions of the square, and effectively showing that when I look at nodal count divided by k and take the lim sup, roughly speaking, the nodal domains that touch the boundary don't contribute in this limit. It's more the ones away from the boundary, but that's roughly speaking. Then in 2009, Polterovich proved that for bounded connected planar domains with piecewise analytic boundary, Pleijel's theorem holds with the same constant gamma 2 as in the Dirichlet case. And you can see the constraints here. So we have piecewise analytic boundary, and that was effectively to give some control on the number of nodal domains touching the boundary, and then they don't contribute to this lim sup nodal count over k. So the next advancement for the Neumann case was due to Léna in 2019. And this time it was for sets in Rn with C11 boundary. And Léna proved that in this case, Pleijel's theorem does hold with the same constant gamma n as in the Dirichlet case. Now, the idea of Léna, well, maybe before I say that, I should have pointed out at the beginning of this slide that, remember, for the proof in the Dirichlet case, the first step effectively was to apply Faber-Courant to each nodal domain and then to use Weyl law. So for the Neumann problem, we of course still have Weyl law, but we can't make use of Faber-Courant here because we have a mixed eigenvalue problem for the nodal domains that touch the boundary. They have part of the domain with Neumann condition and part of it with Dirichlet condition. So there is a hurdle in that we can't just use the same proof as Pleijel, because we don't satisfy the zero boundary condition everywhere. So the strategy of Léna, why this C11 boundary constraint is there, was to locally straighten the boundary and then reflect any nodal domains touching the boundary over that straightened out boundary. And then you would take the piece of the nodal domain where there's a Dirichlet condition, you would have reflected it in the Neumann edge, and you would have got yourself a domain that satisfies Dirichlet condition up to set of measure 0. And then you could apply the Faber-Courant type arguments once again. So the C11 boundary condition was allowing local straightening and then reflect over the straightened piece, and you're back to a situation where you have Faber-Courant, where you can apply Faber-Courant effectively. So then there were some recent advancements pushing it beyond C11, and the first of those was Beck, Canzani, and Marzola in 2024. So they proved Pleijel's theorem in what they called chain domains. So this is some family, a finite family of bounded disjoint planar domains. They have to have piecewise smooth boundary, but they can have corners. So this meant that polygons and other domains with corners are now catered for, that Pleijel's theorem does hold for them. But they also allowed these this family to be joined by thin necks. So there's no convexity assumption in this case either, which will be important later for the discussion. And then there was a further advancement in 2024. So the Beck, Canzani, Marzola results was using a very similar approach to Léna in the sense of this reflection type argument. But of course, anywhere where there was a vertex or a thin neck, a lot more care needs to be taken when defining and then developing the method of doing a reflection. On a very different approach altogether, De Ponte, Farinelli, and Violo considered Pleijel's theorem in the setting of metric measure spaces and RCD spaces, and the results that they obtained turn out to imply Pleijel's theorem for the Neumann problem on Lipschitz domains in Rn. And the approach used by De Ponte, Farinelli, and Violo was similar to the one I mentioned for manifolds by Berard and Mayer, which was using an almost Faber-Courant inequality. And we'll see a glimpse of those ideas when we get to the Robin problem. So I won't say more about it now, but I will say more about it later. Okay, so this is the state of the art for Pleijel, that we do have Pleijel for Lipschitz domains in the Neumann setting. But now we know there's finitely many Courant-sharp eigenvalues for the Neumann case. We can again ask ourselves, how many is finitely many? How big can these eigenvalues be? And this was something that I worked on together with Corentin Léna a little while ago. So you can see I've put some extra constraints on my domain. So this time it's bounded and convex in R2 with C2 boundary. We did get similar results in higher dimension, but the convexity and the C2 boundary we did use quite essentially. The C2 boundary part was so that when I perform this reflection procedure that I described, I can keep track of all the constants. I have a very clear description of the neighborhood near to the boundary, and when we reflect, we can be very precise about the terms that appear there. But let me try to talk more about the result itself. So we were able to show that there are some constants that don't depend on omega, they just depend on the dimension, such that the largest Courant-sharp Neumann eigenvalue is bounded in terms of this constant. And then we have two geometric terms. So one of them is volume divided by smallest radius of curvature to some power. and the other one is isoperimetric ratio divided by the volume. And then for the number of Courant-sharp Neumann eigenvalues, we also have an upper bound of the form where there's a volume term, a smallest radius of curvature, and an isoperimetric ratio. So if I would try to ask myself the same question as we did for Dirichlet, if I have lots of Courant-sharp eigenvalues, does it mean that the domain is long and thin? We don't know from this result, of course, because we've got the isoperimetric ratio, which is the term that would become big if we were long and thin, but then we also have something involving the small radius of curvature, and it could just be that we have a point with a very small radius of curvature, a very high curvature. So we don't know which behavior is it of the domain which would be driven by having lots of Courant-sharp eigenvalues. Okay, and I think the last thing I wanted to mention about this result was that, again, unfortunately, the constants are horribly big, unfortunately. So the constant looks something like 9 times 10 to the 17. I realize that the square doesn't satisfy my hypotheses here of having C2 boundary, but just for comparison, the square would have only had 5 Courant-sharp eigenvalues, so these constants do seem rather big. Okay, so let me move to the Robin case now, and we could imagine that things will only become more complicated. So I have a lot of notation on this slide, so let's go through it together. I stick with my Euclidean domain, bounded, connected, open with Lipschitz boundary. And now throughout the rest of the talk, when I have h, that will be the Robin parameter. It will be a function that's in L infinity of the boundary. So then I'll denote my h Robin Laplacian like this. And the boundary condition now is, of course, that I take the normal derivative of the boundary plus h times u is equal to 0. And I'm always looking in the weak sense. Okay, so I'm just looking at this h. If instead of being a function, if h was just a real number, then we see that h is 0, of course, corresponds to the Neumann problem, and h tends to infinity is corresponding to Dirichlet problem. So these, when h is non-negative, these Robin eigenvalues interpolate between Neumann and Dirichlet. But notice that we're not assuming h non-negative, so we are allowing h to take negative values as well. So that's why I haven't said my eigenvalues are positive, because my h can be negative and then eigenvalues can be negative as well. But in any case, so we know there is still a discrete spectrum in this setting, and we still have Courant's nodal domain theorem. And we also, because of the orthogonality of the eigenfunctions, still have that the first eigenfunction is corresponding to a Courant-sharp eigenvalue, and so is the second one. So we do still have a question around Pleijel's theorem, whether there are infinitely many Courant-sharp eigenvalues or finitely many. So let me tell you the state of the art for the Robin problem. So this time my n has a superscript h to correspond to the Robin parameter. It's still the nodal count. So the first result in this direction was due to Léna in the same paper that I mentioned previously in 2019, using this reflection argument. So it was 4 domains in Rn with C11 boundary, and you'll notice there's a hypothesis on h here, namely that it's non-negative. But the upshot is that Pleijel's theorem still holds with the same constant as it did for Dirichlet and for Neumann. Then in 2024, Hassannezhad and Sher were able to remove the restriction that h is non-negative. They also obtained improved versions of the Pleijel theorem for C11 domains in the same spirit as Donnelly and Steinerberger. So for C11 domains, Pleijel theorem holds without any restriction on the sign of h. Now, in terms of how big can the eigenvalues be and how many of them are there, and together with Corentin, we also got some upper bounds similar to the ones I showed you in the Neumann case, and that was effectively exploiting the fact that we have this interpolation between the Neumann and the Robin eigenvalues. The Neumann ones, when h is non-negative, always give us a lower bound. But of course, you can see here I've got always this hypothesis of h non-negative, and I was using C2 domains because I needed to keep careful track of what happens when I do the reflection. Okay, but we could now ask ourselves, finally coming to my title, does Pleijel's theorem hold for Robin on Lipschitz domains? So we know for C11, but can we extend to Lipschitz? And this was the start of our investigation with Asma, David, and Corentin jointly. And so thankfully, I'm able to tell you that, yes, if omega is a bounded Lipschitz domain, then for the Robin problem, we do have Pleijel's theorem. And with the same constant again as Dirichlet and Neumann case. So I'd like to tell you some ideas of the proof of this theorem, so that you can see how the Robin parameter was playing into the different factors and how we could deal with this case, especially compared to the Dirichlet problem. So the first thing that I would like to do is to think about this quantity lim sup nodal count over k, and to try to understand if there's any cases among the nodal domains, if there's any satisfying some certain geometric property that I don't think will survive as I take k to infinity. So the ones that I don't think will contribute to this quantity. So more precisely, which nodal domains don't contribute to this lim sup nodal count over k. And we can make a straightforward observation that if uk is an eigenfunction for a Robin eigenvalue, and I fix some alpha positive, then I can define the number ni as the number of nodal domains such that the volume of the nodal domain is bigger than alpha. So I'm just effectively trying to say here the volume is not too small in some sense. Then what do we know about ni? Well, we know it's less than or equal to the volume of omega divided by alpha. So we know that this the number of nodal domains with volume that's not too small in some sense, that's bounded by some constant. So when I think of its contribution to the nodal count and I divide by k and then send k to infinity, these nodal domains won't survive. Oh dear, my light's gone off again, I'm sorry. There'll be some nice entertainment for anyone who watches the recording. Okay, so the key point here is that the nodal domains whose volume is not too small, they won't contribute to the lim sup nodal count over k. So the question now is, what do we do about the nodal domains whose volume is small? And we'll follow a similar strategy to that of De Ponte, Farinelli, and Violo, which is to consider the following mixed problem. So I'll keep omega as before, and now I'm looking at some subset U of omega which is open. And on that subset U, we consider our eigenvalue problem, and we impose mixed boundary conditions. So if the boundary of U intersects the boundary of omega, we put Neumann. And if the boundary of U intersects omega, we put Dirichlet. Oops. So effectively, you can see how it feels like it relates to a to the Neumann case with nodal domains inside, that some part of the boundary on the interior is satisfying Dirichlet, and then on the boundary it's satisfying Neumann. And what De Ponte, Farinelli, and Violo showed, and it's in a similar vein to the case of manifolds of Berard and Meyer, is that if for the domains with small volume, we effectively have, in a particular case, an almost Faber-Crown inequality. So I'm going to start the slide from the bottom rather than the top. So you can see here an almost Faber-Crown inequality. Faber-Crown was one of our key steps in the proof of Pleijel's theorem. So when do we have this inequality? Well, it's if there is some neighborhood of the boundary of omega with controlled volume and two constants, theta 0, theta 1, such that the volume of the set U is small in some sense, and the amount which is in the neighborhood of the boundary in terms of volume is also controlled by theta 1. So if we're in this case where both of these inequalities are satisfied, we have an almost Faber-Crown, and that one would contribute to this lim sup nodal count over k. If we're not in that case, well, if we are bounded but we don't necessarily have this condition, well, we still have an appropriate bound which we can use and show that those nodal domains don't actually contribute in the limit to the nodal count over K. So the key idea here is that for this mixed problem, you do in fact have an almost Faber-Cran, and that would end up giving us back the Pleijel constant at the end of the argument. But right now, I haven't said anything about the Robin problem in this particular step of or this particular idea of the proof. We've only introduced the mixed Dirichlet-Neumann problem and shown that there we have almost Faber-Cran. So now we somehow need to come back to dealing with Robin eigenvalues and eigenfunctions. But you'll notice that if I would take UK to be a Robin eigenfunction, then we can use it as a test function in the Rayleigh quotient for this mixed Dirichlet-Neumann eigenvalue. So if we would plug UK into the min-max characterization, it would give us an upper bound here. But now the question is, how can I take this Rayleigh quotient and come back to the Robin eigenvalues? I would like really some comparison involving, so I know on the left here, lambda1 is greater than or equal to the almost Faber-Cran in the case where the nodal domain satisfies those good properties I told you on the previous slide. And what I want on the right is something involving the Robin eigenvalue. So how will we get hold of that one? Well, the idea was to introduce the outward pointing vector fields relative to omega. So if for omega our domain, we'll say a Lipschitz domain, we'll say that F is an outward pointing vector field if it's smooth with compact support, and importantly, if there is a constant that's positive, such that for almost every x on the boundary, the inner product F with the outward pointing normal is greater than or equal to that constant. So effectively, let me show you the result and then I can explain how we get that one. So using this definition, we can now get an upper bound for the Rayleigh quotient on the right-hand side. That looks like this one here in blue. So what is appearing here, there's the Robin eigenvalue, which we were looking for. And then there are some additional terms. So the capital H here, you'll see that that's the minimum between 0 and the Robin parameter, h in L infinity norm. So when the h is non-negative, we won't get any contribution here. The big H, capital H, will be 0. And then it's when the h changes sign that's when this big H will start to appear. And then gamma 1 and gamma 2, they are defined via this outward pointing vector field and the corresponding constant that we introduced. And just a brief word about how we obtained this. So you could imagine looking at the numerator here and applying Green's theorem several times, and at some point using the Robin boundary condition. And once you've got the Robin boundary condition, you can then use this outward pointing vector field to get your bounds in terms of this constant, or 1 over this constant. Okay, and so this piece ended up being the key inequality for proving Pleijel's theorem for the Lipschitz for the Robin boundary condition on Lipschitz domains, because now we have something involving mu on the right and then this almost Faber-Cran on the left. But also it was very useful in addressing our other questions around how many Courant-sharp Robin eigenvalues are there and how big can they be. And so that's what I'd like to show you on the next slide, is a result similar to the Neumann and Dirichlet ones I already showed you, but this time for Robin, where the h, the Robin parameter, need not be non-negative. It can also change sign. So if I take my omega open boundary connected C2 boundary, then we could show that the Courant-sharp Robin eigenvalues are bounded similarly to before. So we have the volume appearing. This delta 1, it's incorporating again this radius of curvature term T plus, and also the cut distance to the boundary, but not just on the interior of the domain, also from the exterior. We have again an isoperimetric ratio to some power, and you see your Robin parameter appearing. So we can get some geometric information from the size of the Courant-sharp eigenvalues. And I'll just mention a couple of words of how we obtained this one, because we effectively exploit the relationship between Robin and Dirichlet eigenvalues. So I'll remind you of some facts you would already know about the counting functions. So first, let me define the Robin counting function like this: the number of eigenvalues less than mu, and then Dirichlet in the same way, but this time we've got Dirichlet eigenvalues. So I'll give the remainder this name R omega d, the remainder of the Dirichlet counting function, where we see our Weyl term appearing here. And then we use the fact that because the Robin eigenvalues are always less than or equal to the Dirichlet ones, we can bound the Robin counting function from below in terms of the Dirichlet counting function. And so if I would now look for an upper bound for mu is of course here, I could obtain that by finding an upper bound for the counting function and an upper bound for the remainder. And in the case of Courant-sharp, a necessary condition for the eigenvalue and eigenpair to be Courant-sharp is for this counting function to be strictly smaller than the number of nodal domains of the eigenfunction. So in order to get our upper bound for mu, we needed the upper bound for the remainder, and we need an upper bound for the number of nodal domains. The remainder one we already computed with Vandenberg previously for Euclidean domains. And then using the same kind of reflection strategy of Léna, you can get an upper bound for the number of nodal domains as well. Okay, so that deals with how big are these eigenvalues, but I could still try to answer how many are there. And with these counting function estimates in mind, we already know that the Neumann eigenvalues are smaller than the Robin ones if the parameter is non-negative, but remember that we're trying to deal with a case where the parameter can change sign. Okay, so here's what we were able to obtain for the number of Courant-sharp eigenvalues. There is some constant C depending only on dimension, such that the number of Courant-sharp eigenvalues in the Robin case is less than or equal to C times these quantities, and they're the ones we've seen before. So we've got the smallest radius of curvature, volume, some power of isoperimetric ratio, and you see here the Robin parameter creeping in. And just a brief word on how we would obtain this. So if I was dealing with H non-negative, I could use that Neumann eigenvalues are less than or equal to Robin, and then I could use that the Neumann counting function should then be an upper bound for the Robin counting function. And it turns out that for convex sets with C2 boundary, you can get an explicit upper bound for the Neumann counting function of this form in terms of its geometric information. But what happens when the H is not non-negative? So if the H can change sign, I can't use the same argument because I don't have any more the monotonicity of the eigenvalues. The Robin ones, some of them will be smaller than the Neumann ones. So what do we do in that case? Well, effectively, we shift everything. So I'll be a bit more precise. Because of the bound we obtained on the Rayleigh quotient, the L2 norm of the gradient of the eigenfunction divided by the L2 norm of the function, we could actually show that if you would shift the eigenvalue in terms of these quantities, gamma 1 and gamma 2, which come from our main inequality in blue from before, you can get an upper bound for the Robin case in terms of this shifted eigenvalue. And that's what we use to prove the upper bound for the number of Courant-sharp Robin eigenvalues. Okay, so let me then come to my conclusions, which is to point out some other questions that I think are interesting off the back of these that I've already presented here. So one thing which is, of course, that we would really like to know that what our methods was if I wanted upper bounds for Courant-sharp eigenvalues on domains with corners, if I'm in the Robin or Neumann case, then how can I obtain those? What happens in this case with less regular boundary? You'll notice as well that I spoke throughout about domains in Euclidean space and not about manifolds. The Pleijel theorem holds for manifolds, for domains in manifolds, as mentioned, Berad Meir for the closed manifolds and for the Dirichlet case, and then Hassannezhad did the Robin case, and our proof would also hold for Lipschitz domains as well in the manifold setting. The issue that I have right now is obtaining upper bounds for the eigenvalues themselves and for the number of them relies on a Euclidean argument at the moment. So I don't know how to get the upper bounds for the eigenvalues themselves or the number of them on a manifold. And the problem for me right now is that this estimate on the remainder in the Dirichlet counting function is very much using a Euclidean argument where we do some Dirichlet Neumann bracketing on cubes and things like this, and then we use the asymptotics for the cube. So it would be interesting to me as well to know how could I get bounds for the domains inside a manifold. Hassannezhad and Sher posed a question in their paper of whether the Pleijel constant is the same regardless of the boundary condition. I think they got some support of this in the particular case of a disk, that they had generically that this should be the case. A big open question, what's the optimal Pleijel constant? So we would like to get to 2 over pi, but right now we're not very close to that one. And there is, of course, that tantalizing hexagonal conjecture in between. And then the next project, perhaps for me in this direction, that we would look at together with Asma would be whether Plejel's theorem holds if omega has infinite volume. So we would, of course, need some extra conditions on omega to make sure the spectrum is discrete. But of course, everywhere in the argument, I was using the volume of omega and moving it around inequalities. So it seems that it should need some new approach to deal with the case of infinite volume. But that's what I wanted to share with you today. So I'd like to thank you very much for listening.
Thank you very much, Katie, for this very interesting talk. So yeah, so we have time for questions. So are there any questions? Let me check the chat.
So, hi, Katie, it's Emily.
Hey, Emily.
Could you give a little intuition when you were talking about the Dirichlet case and you mentioned the hexagonal conjecture with the improved bound? Why are we looking at hexagons?
I think there's a conjecture for the optimal spectral minimal partitions that the hexagonal partition should be the optimal one.
Okay.
And if we could have that, then in the Pleijel argument, rather than swapping lambda1 for lambda1 of the disk, we could swap it for the hexagon.
Which is better. Okay. And then a second quick question. You've assumed convexity and gotten this bound, about then long and thin would be implied. If you assume, have you tried assuming anything stronger than convexity? Like, so in the spirit of this seminar, what if it has some symmetry to the domain?
It's a good question. I honestly know I haven't tried that. Yeah, I mean, so far the impact of symmetry for me has only been with the square, that you have the explicit eigenfunctions and eigenvalues to work with. Would you have any suggestion for which symmetries to start with? Like maybe some symmetric about one axis? Is this?
Yeah, I was wondering about symmetric with respect to one axis.
Yeah, that could be interesting actually. I haven't thought about it, but I think that would be interesting.
Thanks.
In the Neumann and the Robin cases, it was more I kind of didn't point out so strongly that convexity was there, but for Neumann and Robin, when we got these upper bounds for the counting function, we actually needed the convexity to get the upper bounds there for the counting function itself, because we used one of the Weinberger inequalities that the first Neumann eigenvalue is bounded below. And that comes into our argument. We're doing a bracketing, and then we need some lower bound for the first Neumann eigenvalue. So in the case of Robin and Neumann, it was playing a kind of a crucial role in the counting function bounds not being anything to do with Courant-sharp.
Right. Okay. Okay. Thanks.
Thank you.
Thank you, Emily. So, are there other questions? So, maybe a quick question in the in the non-compact case that you mentioned at the end. So, what are the obstacles, sort of, that you said the spectrum might not be discrete? That's the first.
Oh, if I would have infinite volume.
Yeah.
So I think the spectrum we can deal with because we can give some other we could put some other constraints, for example, if there is a suitable Hardy inequality and things in that direction. So I don't think the spectrum I think we can make sure the spectrum is discrete. Yeah, I mean the so on one hand, if I have infinite volume, then a Pleijel, then a Weyl law. The first term of Weyl law includes the volume, so then that part already is not making sense. And just throughout all the arguments in the classic case, we have everywhere volume of omega, and we wouldn't be able to go for the same approach. So that argument where we say, oh well, for each nodal domain we get one inequality, then we add up over the nodal domains and we get volume of the whole thing. So my hope would be that hopefully the bits where it's infinite volume, hopefully there's not. If it would hold, then hopefully there's not some nodal set running away in a complicated way in there and creating lots of nodal sets there. And maybe that would help us if we could somehow sort of restrict the problem back to being something of finite volume, that whatever happens in the infinite part is not contributing too many nodal domains. I think that would be the crucial part, I guess. But right now I don't have anything precise in that direction, just a hope.
Okay, sure. Yes, sure. Yeah, that's very, very interesting. So, okay, yeah, thanks. So I think maybe if there are no further questions, yeah, I would like to thank Katie for giving the talk, and thank you everyone for joining the online talks. And I hope to see you in the next talk. So thank you everyone, and thank you, Katie, again.
Thank you. Sorry, I'm not mobile enough to keep the light on.
Yeah, right. It turns off if you're not if one is